Very good morning, good afternoon and good evening to all the participants and the students who are taking this NPTEL course by the title Multi-Criteria Decision Making. And as you know, this is a course for 12 weeks spread over 60 lectures, and each week we have 5 lectures, each lecture being for half an hour. And after each week we have assignments. So, in totality 12 assignments, and there would be one end term or end semester exam. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur in India. So, this would be the last lecture, not last lecture in the total series, last lecture on the ideas of basically of multi-objective optimization. I will just say a few things and then go into the concepts of multi-attribute utility theory and the concepts of different type of other decision methods, comparative methods, ranking methods like TOPSIS method, Electra method, then Macbeth method, Vicor methods are there, which we will consider. All the whole gamut we will not be able to, but definitely few of them in quite details. Now, why I said that would be the last lecture in the areas of multi-objective optimization, and I told that there would not be any slides, but I will discuss. So, if you remember, we had discussed different multi-object methods, and I told you and I showed you different problems where quadratic programming was solved in the multi-criteria methodologies, and the discussion was there for Pareto optimality, frontier, Pareto optimal points, then concept of linear programming, and then combining linear programming to solve multi-objective problem, integer programming, and all these things were there. And a big part was there about different utility concept, because utility concept what we discussed, maybe you thought that that was disjoint from the concept of multi-criteria decision making, and obviously that thought is quite genuine from your side, considering multi-objective decision making did not consider as such utility functions. Now, the actual utilization of utility functions would be utilized. So, the broader umbrella is multi-criteria decision making, multi-objective decision making we have already considered. Now, we will go into multi-attribute decision making, multi-attribute utility theory, and proceed likewise. This is the 38th lecture. The main coverage for this lecture with 38th one would be multi-attribute utility theory. I will just discuss it conceptually and then go into TOPSIS. So, once I go into TOPSIS, you will understand the utilization of multi-attribute utility theory. So, TOPSIS is one of the methods, and as we proceed, you will see that as I mentioned few minutes back, TOPSIS, Electra, Vicor, AHP will be discussed as we proceed. So, generally when we consider multi-attribute utility theory concepts, so the concept of the multi-attribute should immediately ring a bell, that we are considering more than one attribute or characteristics to understand the concept of utility theory. So, in utility theory, if you consider the ideas we have considered, the quadratic utility function, the general power utility function, exponential utility function, logarithmic utility function, they are all in the cases W was the wealth, and we considered utility based on the wealth. Now, we will consider utility based on more than one such parameters. Consider very theoretically W1, W2, W3 are three variables, based on that we are trying to understand the utility function UW, where W is a vector consists of W1, W2, W3. So, continuing the discussion here, single attribute utility functions are monotonic, where the best outcome is set as 1 or the best one, depending on how the scalarization has been done, and the worst is set at the level of 0, and then the comparison is made. Single attribute functions are developed to describe the decision maker's compromise between the best and the worst alternative. So, he or she is trying to basically make a decision, and given the benefit it accrues to him or her, the person makes the decision and assigns the score or gives the utility function accordingly. This best and worst analysis, if you remember, we have discussed the lotteries, the simple lottery, the complex lotteries. So, based on how the design has been, how you can convert, and we also consider, if you remember, the concept of equivalence, such that given a particular lottery, we can find its expected value, and given the expected value, we can find out that how a sure event can be balanced with respect to the lottery, such that the expected value in both the cases are same. So, under a multi-attribute utility theory, it tends to reduce the complex problem of assessing a multi-attribute utility function into one of assessing a series of unidimensional utility functions. So, rather than have a multivariate case, we will basically break down into different combinations of univariate case depending on how the combinations can be done. Either it can be weighted, it can be multiplied, it can be added. So, depending on the assumptions, it will be done. So, what basically MAUT, multi attribute utility theory, does, it is basically a functional form which stitches or joins these unidimensional utility function in such a way that it presents in front of you a multi attribute function, such that given all the attributes, you can immediately understand that how they can be analyzed from the point of view of the univariate case. It is basically a way of trying to replicate or present the multi attribute concept using unidimensional case, because it will be easy for us to basically function. As I said, I will only discuss the formulas, later on we will consider them as we proceed with the problems. The main problem under multi-attribute utility theory, as I said, is basically to find the utility function u x, and here x or w, whatever we have been utilizing, x is basically the variable and it is not a scalar, it is a vector. So, x vector basically has x 1 to x n. So, we want to basically find it, and that is the multi-attribute utility concept, which, as I mentioned few minutes back, can be broken up or stitched from a univariate utility function case. A simple method could be to derive a function such that I know, or we are aware, that the utility function is given by some functional value f. So, depending on the parameters here, now it is more of u1, u2, u3, u4, where u1, 2, 3, 4 are the corresponding utilities based on the univariate case. So, even though that may not be correct, but let me say consider that, say for example, the univariate cases are quadratic and exponential. So, given a multivariate case, we can break it down into different types of univariate quadratic and univariate exponential utility functions and solve the problem accordingly. This is more from the problem solution point of view. One of the simplest way of decomposition is the additive function. So, you have different utility functions, you add them up, like if you remember the case where we have considered the objective function or the multivariate case, the multi-objective optimization case. So, there were two options if you given. So, given f 1 and f 2. So, which are the objective functions? I am considering only two. So, you can optimize f 1 or f 2, bringing the other objective function as a part and parcel of the constraint, or else case 2 method is you combine f 1 and f 2 in a convex combination way, that means give weightages of lambda 1 lambda 2 to f 1 and f 2 respectively, such that the weights add up to 1. Weights means lambda 1 plus lambda 2. So, in the similar way, rather than have the multivariate utility function, we basically have the univariate case, add them up and give weights accordingly, such that the corresponding weights are from lambda 1 to lambda n, and the weights are given in such a way that combining the addition of u 1 into lambda 1 plus u 2 into lambda 2 till the last utility function which has been considered, depending on how many such univariate cases are there, you can basically present the multivariate case. That is a very simple way. So, another parameter which is also used is basically depending on the scaling factor. So, what is the scales you want to give? What is the overall effect? So, you want to scale it up or down. So, here lambda 1 to lambda n which are considered are normalized depending on the weights you want to give. So, say for example, I am giving a weights of lambda 1 to lambda n as between 0 and 1. That means, the addition of lambda 1 to lambda n is 1. So, all of these weights which are basically lambda 1 to lambda n has been normalized in a sense, or you have considered the normalized weights such that they add up to 1. And if you want to scale them up, you basically multiply or divide depending on whether the scaling is positive or negative, such that we are able to get the scaling factors also included as part and parcel of the univariate utility function, and add them to find out the multivariate or multi-attribute utility function. The scaling factor assures that the compound utility function u assumes values in the interval between 0 and 1. So, if you consider the properties of the utility function in general should hold true for the univariate case, and it should also hold true for the multivariate case. In the same way, like say for example, if you have a univariate distribution and a multivariate distribution, all the distribution properties, fundamental things from statistics should hold. In the same way, the univariate and the multivariate utility function cases, the properties would definitely hold. So, without going to the problem, which as I said, I am again repeating, they would be coming up later on. So, I will just state the models and state the important facts or what are the important points to remember. So, you have the additive utility function. So, in that case, and consider the utility functions are n in number. The first one is that where you add up the utility functions. So, this would basically become u x 1 to x n, and this basically is combined by adding n number of utility functions, the simplest one. The next one is the weighted additive, which means that you first multiply with the weights we just discussed and then add them up. So, if I consider technically the weights here, by the way, if you see the first additive case, there immediately the idea would come out that the weights corresponding to each utility functions lambda 1 to lambda n are all 1. So, now if I basically give the weights lambda 1 to lambda n, where all of them are not 1, you have the weighted additive utility function given, where n is the number of utility functions as general, and there are other n number of scaling constants also, which basically add up each individual utility function value to be combined, and in the end give you the multi-attribute utility functions. The third and the fourth one models are considered as the multiplicative, because you multiply the factors, or log additive, and the fourth one is quasi additive, and I will come to the utility functions, and also in the third column the number of calculations or the number of important points to remember of that. So, if you consider the utility function, the multiplicative or log additive, so there are many terms. So, consider this is the first term which I have underlined with dark, a little bit dark yellow, then there is the second one which I am underlined by red, then is the dark blue, and so on and so forth. Now, if you pay attention to the first one and ignore the higher terms. So, this is just the last example which we got, which was the or discussed, which is the weighted additive. Now, the multiplicative term, if you see, they are coming from the fact that, like, consider the expansion of a Taylor series in the multivariate case, or just a expansion in the multivariate case of any series. So, the terms which come up, consider there are n. So, if I consider n number of them, so they can be combined in NC2 number of ways, and if I consider combination with itself is also allowed, then you will have basically the whole set of combinations which are possible. So, if I consider these concepts, and here I is equal to 1 to n, where n is the number of such univariate case, j is also 1 to n, and in this case if I assume, or if I try to visualize the variance covariance matrix. So, the principal diagonal of the variance covariance matrix is what? Is basically the variance or the covariance with itself, and the of the diagonal elements are the covariance of ith to the jth one, and it is multiplied by 2 because they are symmetric. In the same way, if we consider, depending on I is equal to j and I is equal to not equal to j, you can basically replicate, and this is of the second order. That is why the word multiplicative, you basically get all the terms accordingly. So, obviously, it become complicated, but depending on the simplicity, we will only stick to the simple additive model. And if you look at the multiplicative one, obviously, the higher orders can also be considered. So, in the higher orders means when you are taking combination of 3 out of n, NC3. So, if I consider NC3, the corresponding parts which is very simple to understand, you are taking lambda I into ui as the first. So, ui is basically the first utility, lambda I is the corresponding factor to be multiplied, then uj multiplied by lambda j, uk multiplied by lambda k. So, these I am just putting a tick mark, lambda I, then ui, then I am using the green color, lambda j into uj, then I use the violet color, lambda k into uk. And similarly, if I go, I can have 4 terms, which means, and by the way, another thing which I missed as I was going. So, if I consider there is k square, so depending on the factor which is being multiplied, and this factor of k, if you remember, that was basically in a way given as the scaling factor which you can consider. So, if you see the scaling factor here when we started. So, scaling factor being k means you are giving the scales for each of them in the single case as only of one order, then k square means you are basically multiplying the scaling factor of both. So, it may be possible if both the scales are to be increased. So, obviously, both of them will be multiplied and increase the value, or else it can decrease the value depending on the values of k. In the case of quasi additive, you consider the weights as lambda I j depending on the ideas you are going to consider for the multi attribute. So, coming back to the multiplicative or log additive, you have n number of utility functions and n number of scaling constraints. For the quasi additive, there are n number of utility functions and 2n minus 1 number of scaling constants, because the scaling constants are not lambda i's now themselves, they are lambda I j depending on how the scaling the factors have been taken into consideration. And also, if you only concentrate on the first term, it remains and continues to remain as the simple additive model. When I consider the bilateral one, the corresponding functional values are actually dependent on the functional value of f. So, bilateral one, hybrid one, if you consider, the factors can be increased. So, depending on number of terms you are considering. So, the second term where I put a tick mark, it is of square order 2 terms. Where I put a double tick mark in red, it is cube, and if you can understand the cube means it is being summed up from I is equal to 1 to n, j is equal to 1 to n, k is equal to 1 to n, but obviously the double counting. So, j should be greater than I and k should be greater than j. And as usual, the first term which I circle with the violet color is the simple additive one. In the hybrid one also, the Fn is the number of scaling constants, where f is some function which depends on n, and these scaling factors or hybrid is basically combine them accordingly to achieve the utility function. So, these I am just mentioning, but detailed discussions are outside the ambit of the course. So, you have the quasi pyramid and semi cube. So, if you consider, so the pyramid structure like this, where the base is a triangle, or else if you consider the base is a square, the pyramid structure would be there, and the layers which you can take, which will give you the different factors which are there in the extension, can be understood as you take the slices of the pyramid accordingly. Similarly, for the semi cube one. So, I am not going to the details. So, also again another point, the first term in the quasi pyramid and the first term in the semi cube are the simple weighted concept of utility function. Univariate weights are taken, multiplied by the factors and scaled up to find out the overall multi attribute case. So, for the quasi pyramid, number of calculations is n into n minus 1 by 2, and with non separable interactions is there, and Fn is the number of scaling factors. Similarly, for semi cube, Fn is the number of scaling constants, where the function f is some function which depends on n only, in the same case as like the other one. The interdependent one would be the case where, rather than having the univariate case, your main focus is now the utility functions which are dependent. So, rather than having u I u j multiplied separately, it is a bivariate case. Bivariate means I am using the statistical term, is basically a utility function where both the parameters or the variables are x I and x j. I and j are basically the counting between I 1 to n. Similarly, if I consider the third factor, it is u I j x I x j x k. So, it is basically not independent, but they are interdependent depending on the order we are taking. Similarly, for the fourth term which is not written here, it will be u I j k l. So, I j k l, which are the four terms, and the parameters or the variables which will decide the utility functions would be x I, x j, x k and x l. So, generally the fourth term, which as I said is not written here, I am not writing the lambda part. So, I j k l. So, there are four terms, this is x I, x j, x k, x l, and f is some function which depends on n, depending on how the utility function has been developed. In the multilinear one also, before I go to the multilinear one, so this would have become much clearer now. The first term is basically the simple additive utility function. For the multilinear case, you have again the first term is the additive one, and the factors which are there are built up. So, if you consider the second term, generally for the earlier case it was basically lambda I, lambda j, lambda k, and then it was u I, u j, u k. Here ui, uj, uk remain the same, but the factors lambda I, j, k are expressed as lambda I, j, k all together, which are dependent, and there you will get 2 n minus 2 to the power n minus 1 number of scaling constants to be included. Now, the reader or the students or the participants should know two important points about MAUT without going to much theoretical concepts, that there is a preferential independence concept, that is the pair of attribute x and y is preferentially independent of z if the value trade off between x and y is not affected by a given level of z. So, consider x and y are there, and if I basically try to incorporate the ideas of a independent attribute function z in both of them, the corresponding ranking concept would not change. So, which we will see later on, and it has already been discussed in one of the properties or the axioms, if you remember, when we are considering the earlier part of the course. And the second point is utility independence, where attribute x is utility independent of y when conditional preference of lotteries on x given y does not depend on the particular level of y. So, depending on given a condition that y is changing. So, obviously, the preference of the conditional preference of lotteries based on x would not depend on what is the state of y independent. One can also use goal programming to address the issue of MAUT. So, if you remember, in the goal programming we had the objectives, and the constraints were less than type, greater than type, equality. So, here let us consider the criteria which are k in number, and they are denoted by f1 till fk, and I divide the overall k is basically a number, it can be 13, 14, 40, whatever. I divide into 3 sets, in the sense that they are distinct. Interaction between these 3 sets which are elements of k is a null set. So, I consider the first set from f1 to fk1, k suffix 1. The second one, I will use a different color, is from fk1 plus 1 to fk2. The third one is basically from fk2 plus 1 to fk3, such that the sets are, I am marking, this is the third one, this is the second one, and this is the first one. So, this is what I mean. So, union of them is the k, and k1, k2, k3 are all distinct, such that the interaction between k1, k2, k3 is a null set. Now, the question is that when we consider the criteria functions, would it be true that all of them are independent? Answer is no, but we will consider it to be one of the assumption based on which we will try to proceed. The question would be consider the dependence structure, like I want to. Now, if you remember, the examples which would be discussing are more qualitative in nature, subjective in nature, discrete variables. So, consider you are buying a car and mileage and maintenance are dependent, or cost and maintenance are dependent, or cost and mileage are dependent. Higher the cost, better the car, we assume, and better the mileage. So, mileage is positive, increasing, better for me. Cost increasing, obviously is not better for me, because I have to pay more. So, obviously, there is a dependence between these two criteria, and when I mention mileage, when I mention about cost, these are the criteria which are used to decide that what are the important factors based on which you are going to buy the car. Another factor consider for the housing, or for say for example, selecting the college where you will study or where a person will study for higher studies, be it commerce, engineering, MBA, sciences, whatever it is. So, consider the buying the house, if the locality is good which you want, positive feedback, safety, nearer to bus stop, nearer to metro, obviously the cost is higher, maintenance is higher. So, the point which is mentioned that they are independent would not be true in many of the examples, but we will still consider that to be true and solve the problems accordingly. So, with this I will end this lecture and start with the discussing of more details about one of the methods one by one, as I mentioned, TOPSIS, Electra, Macbeth and so on and so forth. Have a nice day and thank you very much.